Hi, I'm DJ Ware. On this episode of the Cyber Gizmo, I'm going to be looking at exokernels. Stay tuned right after this. Exokernels. What are we talking about here? I've had a couple of. I had an old video. I think it was last year or so, where I talked about I was going to get into exokernels and pico and nanokernels, and so I'm going to start with exokernels, and we'll go through those as to what they actually are. So exokernels is kind of interesting, and it was initially started by MIT as a research project. This whole thing is normally called an exokernel OS, but we're going to talk about four different questions. First, what is it? What is an exokernel? Second, are exokernels better than traditional operating systems? And then third, how do they work? And fourth, what are the advantages and disadvantages of an exokernel? So let's look at it from the standpoint of a traditional operating system like Linux. I mean, you can also pick on macOS or Android or even Windows, but traditional operating systems always abstract and protect system resources. So there's a hardware abstraction layer that prevents physical access to the device. And so the view that is presented to applications is this virtual device as well as the operating system itself. So a traditional operating system abstracts physical memory into virtual memory. So in other words, the paging schemes and all of that is all handled within a virtual memory. And I've talked about this before in the internals for Linux. They also abstract the disk into virtual file systems that allows them to, on top of that model, place additional file system types such as ext4, btrfs, zfs, and so forth, xfs. But then that view of those disks is actually the partition, and then from the partition you go to files and directories and all that stuff. So they also abstract the CPU into processes and threads, and then there's also a scheduler piece that schedules activity for those particular applications to execute. And then there's a timer that's set to say, okay, your time's up, and I'm taking it back. The benefits of the traditional operating system is it provides a portable interface to the underlying machine. An application are unconcerned. They don't have to worry about all the intricate details about handling and accessing hardware management. It's all done for them by the kernel. The application developer then can just concentrate on the critical functions or the functionality of their application without having to be concerned about overall management of the system. So this leaves us, though, with a serious problem. And the serious problem is that only privileged servers and kernel can manage system resources. Well, wait a minute. Isn't that the design? Isn't that the purpose? So why is that a big deal? Well, applications are restricted to the interfaces and implementations that is offered to them by the privileged software. In other words, the kernel, the only thing that an application can do with a particular hardware resource is whatever the kernel presents to it. It doesn't have the choice. It can't, if it needs additional or more finer grained application management of that hardware resource or system resource, it can't do it because it's not provided for them in the kernel. So why is that a big deal? That's a big deal because security cannot be fine-grained. Also, security is limited to the virtual device. When you look at how Linux, for example, implements all of its ACLs and security controls, they're done on the virtual device, not the physical device. So there's a gap that's left open for someone to infiltrate and inject malware through. Have people done that yet? Yes, there have been occasions where people have directly bypassed the kernel's ability to handle virtual file systems. And we'll talk about that some other time, but not yet, not at this time. So disk access has the same problem. And And I personally ran into this on a project where we were attempting to protect particular resources that were on disk based on the ACL level of a user. And there was a couple of things that occurred. There was requirements that users could be members of multiple ACL groups. Well, that's fine. I mean, that's not a big deal to handle. But if you weren't a member of that group, you could not even see the indication that the file was there. So if you were accidentally exposed the directory and that file appeared, even though they may not have read access to it, then you failed the requirement. So that particular file couldn't even exist, and it was dynamic. It changed based on a date. So say 10 days it would be at this level, and then 25 days it would be at the next level, and past 30 days it would be at a different level altogether. So it was a moving, it was a moving target, and we're not talking about just, a few hundred files. We're talking about thousands and thousands and thousands of files. So, yeah, I mean, that was a problem. To go back and to reset the access levels, you couldn't do that with ACLs because you would have to go manage every file on the file system, and that just wasn't the right way of doing it. So, yeah, if we had had better access controls and more finer grained ones, we probably could have pulled it off. But because of the way Linux is implemented, it wasn't performant. I mean, yeah, it could do it, but it wasn't performant. Also, memory access can't be fine grained either. You have the same problems. Yeah, if the image was in memory or the file was in memory, again, the access levels applied to it. Well, that doesn't work. That doesn't work. So, yeah, I mean, there are times when there are things you need beyond what the particular operating system offers to it. Well, how could the traditional operating system handle that? Well, it could be designed to accommodate every application and anticipate all possible needs. It reminds me of a requirement I got one time that said, and would you support all future developments in this area? It was like, what? How do you test for that? I mean, that just wasn't going to work either. I mean, yeah, you can't have a requirement like that. It just doesn't make any sense, because how do you anticipate what every possible application is going to need? So the generation of, even if you could develop such an interface, that interface would need to resolve all the trade-offs, and it would have to anticipate every application developer's needs in the future. And this is known as an infinite automation problem. That is, it's one that is not solvable. I mean, it's an unsolvable problem. So, yeah, I mean, that just won't work. So that's what Exo Kernels were designed to solve. And they give the application code as much control over system resources as possible without compromising the system security or integrity of the system as a whole. So basically what you're doing is you're separating system protection from system management. So, yeah, and the application developer gets to choose how to manage the resources on the system. In other words, they're now acting as a privileged resource. Even though they're not really a privileged resource, they are acting like one. So that gives them the freedom to innovate within the system, the protections provided by within the systems protected by the application kernel, or the systems kernel rather. So, and that removes this overhead, as you can see here. That is a syscall dance on, I think that's Microsoft Windows. But that's a syscall dance that occurs, and you can see it's nuts. I mean, if I were to draw out the flow diagram and the state diagram for it, you would see that with all of the things that goes on with a syscall handle and the error traps and how it manages all of that, what happens when the device is busy, how it reschedules that syscall. So yeah, whoever first called this a sys trap handler, they got it right. It is. It's a trap handler, all right. It's a trap. It's a trap. Yeah, so what is this exokernel? What the heck is this thing? So it exposes low-level hardware devices to the application. That's what it does. It makes it available. There is no virtual hardware abstraction layer. The application gets direct access to the hardware. Whoa, wait a minute. Whoa, whoa, whoa. What happens now? Well, there is a protection level that prevents things from getting out of hand. I mean, if an application crashes, you don't want the entire system to go down. So the exokernel is managing that kind of an aspect so that if the application just out of a sudden bombs out, then you don't lose the application, you don't lose the entire system. The other thing is that multiple applications can share the same hardware resource at the same time. Yeah, I did say that. You can try that on Linux with a graphics card. I mean, yeah, you can do it, but you're actually doing it through another layer. The window manager has to do that for you because really only one device is handled by one application within the syscall system interface. Yeah, you can send messages to it through syscall, sure. But the actual device that's managing it is up the chain somewhere. Yeah, so you're interfacing with an API. Whereas in this case, you actually have a mechanism to share the hardware devices between applications. So that makes the application potentially as powerful as a privileged kernel and a server. So yeah, I mean, so for example, in memory, an exokernel could provide the physical pages and blocks used for paging. Oh, wait a minute. You're just like, wait a second. Yeah, it's an operating system function, isn't it? Sure. But there are times when you might want the application to do that. Now the application can say, oh, I don't want to deal with this. It might defer the rest of memory management to the kernel, or it might defer application management, the system resource management to the application. It depends on what the application needs are. So, like, for example, the application could do part of the things. It could do page allocation. It could do fault handling. It could do the page table layout, for example, depending on what it needs it to do. So, well, okay, so wouldn't that be chaos? Or no, it would be if you didn't have some way of handling it. Yeah, it would be chaos. Um, the exokernels that have been implemented provide something called libOS. And libOS contains the APIs for the application to use, and it allows it to share code to provide access to the physical system resources from multiple apps at the same time. By the way, the kernel is also considered an application in that space. And it has also libOS as well as some other functions that allows it to handle the protection levels for the system. So yeah, so you got the same libOS that's provided to the exokernel. So if the application developer doesn't want to control and doesn't need to control the system resources, he can defer it. They can defer it. That is back to the exokernel to do. Why is this a good thing? So it provides a huge performance boost, and it allows scalability. I mean, if you look at, I mean, just the way, I mean, I've talked about this before, but if you look at it in networking where you're doing interrupts on every packet, so consider networking where you have high-speed networking cards. The faster that networking card goes, the faster the packet rate is. The faster the packet rate is, the faster the interrupt into the system is. The more system calls that are generated, the more context switches that occur, and you basically are starting to bottleneck the system just trying to manage the inflow of data. Well, that's not good. So the other thing is that applications can defer, or they can reuse the libOS code, or they can even extend it. So if they don't like the way the system is managing the resource and they have a specific need, maybe it's the application that is sent by the people that developed the network card, then they would have finer control over it. So the kernel maintains control over the security and integrity of the system still, like I said. So that's why it's better than a traditional kernel for this particular point of view. So how do they work? So there's an example diagram here of how it would work. There's GCC up there. That's an application that has both virtual memory and the file system. And it is managing it through libOS. So you have the virtual memory, the net, and the file system that it's managing here. And then over on the other side, you have the specialized WW server, which is going directly to manage the network and the file system via libOS subsets. So, um, yeah, that's basically how it's working. So the Exokernel provides fault isolation, that is, an error in the libOS. The Exokernels provide these operating system functions, provides fault isolation so that an error in libOS is restricted to the application currently using it. It doesn't take the entire system down. There's also coexistence, and what do we mean by that? We mean that by design, multiple, possibly specialized library operating systems can coexist on the same exokernel. Now, conceivably, with exokernels, you could have Windows applications, Linux applications, Mac applications running on the same machine. Now, it would. I'm not saying that it wouldn't take some doing to get people in a room and go, okay, you guys need to hammer out an API that's the same for all of you, so that we don't have a giant libOS. Half of it's in Windows and the other half of it's in macOS, and then we leave a sliver for Linux. So yeah, I mean that's just not going to work. But within the same operating system, you do have coexistence for sure because they are sharing that same code within the library operating system. So security, Exokernel maintains control over all the security controls over the resources, and applications can extend that security to provide finer grained detail when it's needed. So my problem where I had different users with different access some of them could see it, some of them could view it, some of them couldn't, some of them could change it, some of them couldn't. And then that would change based on a whim or a mandate that could change on how the access to that was granted. So yeah, and then scheduling, the Exokernel maintains control over the scheduling of the CPU. So yeah, so you do avoid some of the chaos. So the long and short of it is that exokernels maintain the protection of resource the applications manage it. That's simply it. Exokernels expose hardware to the applications. Exokernels expose the allocation of resources to the applications. And exokernels expose the revocation of resources to the applications. So the applications could revoke access to the resource. The exokernel could revoke access to the resource. And yeah, that's how they work. So exokernels protect resources using fine-grained controls. For example, an exokernel can protect disk blocks and not just disk partitions, which is what it does today under Linux, the actual kernel. So exokernels expose names for the devices, not some cryptic hieroglyph mechanism that takes the random channel and some number and says, okay, this is it. And you have to guess where it is in this particular time. I've seen some really crazy things with USB devices. I even remember there was an LSI controller on a Sunbox once that every time you rebooted the system, it reordered the device numbers. So it was like, huh? Why is it doing this? I mean, so you could have your file systems in some crazy attempt to try to mount things which didn't exist. So, yeah, I mean, you don't need that. We need names, and names makes it a lot easier to know what you're dealing with. Exokernels expose the information. The kernel provides system information to the applications that would be hard for the applications to collect on their own, like fault information about what's going on with the device, maybe the temperature of the CPU, or maybe the current clock setting of the CPU, for example. So yeah, I mean, those are things that it could provide. The advantages of an exokernel is it minimizes hardware abstraction. Why is that a good thing? It allows me to reduce the overhead by removing system calls. It also provides the application of the free application developers with the freedom that they may need to manage system resources on their own. Plus, it offers a finer grained protection level that we just don't have today. Yeah, you could do it, but you still would not be direct against the hardware. You would be direct against the virtual device. So yeah, it also permits shared access to system resources via libOS. And the diagram on the right is an example of EXOS, which is a research operating system. It's long defunct, but That allowed a Unix application and a specialized application to manage the same disk drive, and they were sharing access to those blocks and reading and writing to that particular drive at the same time. The disadvantages of an exokernel, not enough research has really been done to flush out all the unknowns. Typically, research in operating systems takes some time in order for them to figure out, oh, well, the things that I assume will work the same aren't working the same. So, yeah, I mean, things like Linux have gone through a lot of research, and a lot of that I mean, a lot of that was flushed out years ago. But the current systems that are around that support exokernels are research operating systems. They're not commercial, and so you wouldn't know what the commercial interactions would be until you started to experiment in those areas. So yeah, you wouldn't want to just grab one of those and just start using it in production. That would probably be a really bad idea. So the other thing is granting direct access to system resources to the application. That's counter to current security thinking. So yeah, and the reason why they think like that is because of the way the systems are wired today. So and having direct access to the system resources, do you really have direct access, or are you really just accessing it through libOS? That's really the question. So the other one is how to multiplex different security protections for the same resource. My problem that I had with a particular solution set that we developed. So, for example, the same disk block could have more than one security definition depending upon the application's workload. And that workload could change over time. It's dynamic, right? I don't know what applications are going to be running next to me in memory. I mean, especially if I'm in a cloud environment, that could be anything. Infinite extensibility is a problem. Infinite, and that's basically what you're talking about here. That requires something called Turing completeness. And Turing completeness, as far as I know, has never been done. Now I'm talking about, when I say commercial OS, I'm not talking about one that's paid for. I'm talking about one that exists out in the business stream today. Linux would be considered a commercial OS, even though it's open source. That's fine, but it is considered ready for production workloads. Windows is a commercial OS. MacOS is a commercial OS. Also, so is Android, and by the way, Fuchsia now is too. So one of the things that one of the things that Exokernels allows, since we are is infinitely extensible here, is we do allow dynamic downloading of code. Now, that means that the OS will cryptically download applications that the applications want. And if it's not installed already on its own, it'll it'll install that along with its own version and copy of itself and the system libraries that it's using on first demand. So, and that pretty much describes what Fuchsia OS does today. When you type in ls, for example, on the command line, ls doesn't exist to the system. So it downloads ls along with the libc libraries and some other things that it might need, and its own versions that were developed, that were created when that ls was compiled. So, and those are maintained in its own library. So if you download something else that uses those same libraries in a different version, for example, those other applications won't use those libraries that the ls downloaded because they're in protected space. So, yeah. So anyway, the Linux BSD, of course, we all know, uses package management, and that can be a problem because it depends on what versions of the supporting libraries are in that package. Those could be newer versions, they could be older versions, and they can overlay what's currently on your system, and that could introduce unexpected behaviors in applications that are depending upon a certain version of that library in order to work. I mean, you can and removal sometimes can be a disaster with a package management system when one of the package management systems goes completely rogue, like APT did for Linus on Linus Tech Tips when he was using Linux for a month and went to uninstall OBS on Pop! OS. He also removed the window manager and all of Even X11 went with it, so he lost everything. And that is an example of what happens when a package manager goes rogue under Linux. That would not be possible on Exo kernels or even on Fuchsia OS because those are maintained in their own space. So it would just remove that protected version of the app and then it'd be done. The other thing that we've seen is that we've seen spoofing digitally signed keys to bypass OS checks to install malware disguised as legitimate software updates. We've already seen that. So that would be a concern here too, that we'd have to be very careful not to expose those cryptographic keys to the general world outside of the application developer in order to prevent impersonation attacks from occurring. So, I guess in a summary, what is an exokernel? An exokernel is a kernel that allows me to get rid of hardware abstractions. And it gives more power to the applications and allows them to manage in their space. Now, the question is are application developers likely to jump up and go, oh, yeah, this will be great. This is exactly what we want. Possibly they might, particularly if they're game developers, they might. Or if they're doing specialized applications that require finer grained controls, they might be interested in that. And they're looking for higher performance. And the second thing is it allows me to get away from the syscall dance. The syscall dance can be a performance nightmare. It can actually eat up your system if those are occurring at a very rapid rate. And a lot of times that'll prevent you from scaling. Now, Linux can scale quite well on its own, but there is a cap that it reaches, and then if you notice the high performance guys start going to clustered machines. So yeah, I mean, there isn't an infinite cap. Eventually you run out of the ability of the system to manage on a single platform. So that's pretty much what I had today. I mean, it's an interesting thing to look at. Do I think Linux should just abandon what it's doing? No. But I brought this topic up. I thought I would talk about it a little bit, some of the advantages and some of the disadvantages. The disadvantages, of course, to exokernels is there's a lot of unknowns. I mean, it hasn't been placed into an environment at all in which real world applications and users are going to be hammering on it. We haven't introduced it into this world of security that we have today. And so there would have to be some current thinking that would be brought in order to be able to bring it up to date. Exokernels have been around since 1997. There's a couple of research kernels that are around. XOOS is one. There's also XOK. I don't know if EXOS is still around or not. That might be. I would have to go look, but I do know the other two are still around. So I hope you enjoyed this today. At least maybe a little familiarization with what exokernels are. I hope you enjoyed this, and if you did, please like and subscribe. Hope to see you all again real soon. Bye for now.